10.9 Convergence of Taylor Series. The outline of this video is as follows. First, we will introduce the central concept of Taylor's theorem and the resulting Taylor's formula, which provides a way to represent functions as infinite series. Next, we will focus on a critical component of this formula, the remainder term. Understanding this term is the key to determining if a Taylor series actually converges to the original function. Building on that, we will then present the remainder estimation theorem, a powerful tool that allows us to find an upper bound for the remainder. After establishing these foundations, we will see how to perform algebraic operations on Taylor series. Finally, we will apply these ideas to a practical problem, estimating the error that occurs when we use a finite polynomial to approximate a function. Taylor's theorem is a crucial result that provides a precise mathematical form for the error in a Taylor polynomial approximation. Let us break down the formula presented here. The equation states that the function's value at b, f of b, is equal to its nth order Taylor polynomial, plus one additional term. This final term is called the remainder, and it represents the exact error of the approximation. Notice its structure. It looks just like the next term we would add to get the n+1 st degree polynomial, but with a key difference. The derivative is evaluated not at our center point, a, but at some other number, c, that lies between a and b. The theorem guarantees such a, c, exists, even if we do not know its exact value. As noted, this is a generalization of the mean value theorem, which is simply the case where n equals 0. The essential takeaway is that Taylor's theorem gives us an explicit formula for the remainder, which we can use to determine how accurate our polynomial approximations are. We can now reframe Taylor's theorem into a more practical form called Taylor's formula. This version is powerful because it treats the endpoint of our interval not as a fixed number, but as a variable, which we will call x. This allows us to think of the Taylor polynomial as a function that approximates our original function, f of x. The formula states that for any x in an interval containing our center point a, the function f of x is equal to its nth degree Taylor polynomial, which we call p sub n of x, plus a remainder term r sub n of x. This remainder term, also called the error term, gives the exact difference between the function's true value and the polynomial's value. The formula for this error is given by the n plus first derivative of f, evaluated at some number c between a and x, divided by the quantity n plus 1 factorial, all multiplied by the quantity x minus a raised to the power of n plus 1. The key insight here is that Taylor's formula provides both a polynomial approximation and a precise expression for the error involved in using it. This slide presents the crucial link between a finite Taylor polynomial, which is an approximation, and an infinite Taylor series, which can be an exact representation. Recall that Taylor's formula expresses a function, f of x, as the sum of its nth degree polynomial and a remainder term, r sub n of x. The Taylor series is what we get when we let n go to infinity, including all possible terms. For this infinite series to perfectly equal the original function, that leftover piece, the remainder, must shrink to nothing as we add more and more terms. Therefore, the Taylor series converges to f of x if, and only if, the limit of the remainder term as n approaches infinity is 0. When this condition holds true over an interval, we can confidently state that f of x is equal to the infinite sum shown on the slide. This is the fundamental test for convergence that we will use in our upcoming examples. Let us work through a key example to show that the Taylor series for e to the power of x converges to the function itself for all real numbers. This is critical for confirming that the series is a valid representation of the function. Recall that Taylor's formula expresses a function as its nth degree polynomial plus a remainder term. Our goal is to prove that the limit of this remainder is 0 as n approaches infinity. The remainder's formula contains an unknown value c, which is somewhere between 0 and x. We can solve this by finding an upper bound for the term e to the power of c. If x is non-positive, then c is also non-positive, so e to the c is at most 1. If x is positive, then c is between 0 and x, so e to the c is less than e to the x. In either case, the remainder's magnitude is bounded by a constant times the fraction x to the power n plus 1 over n plus 1 factorial. This fraction goes to 0 as n goes to infinity for any x, so the remainder must also go to 0. This proves the series for e to the x converges to e to the x for all values of x. The remainder estimation theorem provides a powerful and practical tool for determining the maximum possible error in a Taylor approximation. Recall that the exact formula for the remainder, r sub n of x, involves the n plus 1 th derivative evaluated at some unknown point, c. This theorem helps us work around that uncertainty. The main idea is to find a single, constant upper bound, which we call m, for the magnitude of that n plus 1 th derivative over the entire interval between a and x. If we can find such a number, m, then the absolute value of the remainder is guaranteed to be less than or equal to m times the quantity absolute value of x minus a raised to the power of n plus 1, all divided by the quantity n plus 1 factorial. For example, with the function sine of x, all of its derivatives are bounded by 1, so we can always use an m value of 1. This inequality is the key to proving convergence. If this upper bound goes to 0 as n goes to infinity, then the remainder itself must also go to 0, and the Taylor series converges to the function. Let us now use the remainder estimation theorem to prove a very important result, that the Maclaurin series for sine of x actually converges to the function sine of x for all real numbers. The first step is to find an upper bound, m, for the derivatives of our function. The derivatives of sine of x cycle through cosine of x, negative sine of x, and so on. The key insight is that the absolute value of any of these derivatives is never greater than 1. Therefore, we can choose m equals 1 for our estimations. Now we apply the theorem. For the sine series, which contains only odd-powered terms, we look at the remainder r sub 2k plus 1. The theorem tells us that the absolute value of this remainder is less than or equal to m, which is 1, times the absolute value of x raised to the power 2k plus 2, all divided by the quantity 2k plus 2 factorial. The final step is to check the limit of this upper bound as k goes to infinity. For any fixed value of x, the factorial in the denominator grows much faster than the power in the numerator, so the limit of this expression is 0. Because the remainder term is squeezed to 0, we have proven that the Maclaurin series for sine of x converges to the sine function for every value of x. Now, let us apply the same logic to the cosine function. Our goal is to prove that the Maclaurin series for cosine, which is a Taylor series centered at 0, actually converges to the function cos x for all possible values of x. Just like the sine function, the derivatives of cosine are simply negative sine, negative cosine, and positive sine cycling through. The absolute value of any of these derivatives is never greater than 1. This allows us to again use a maximum bound of m equals 1 in our remainder estimation theorems. The Taylor formula for cosine consists of its even-powered polynomial of degree 2k plus a remainder term, which we call r sub 2k of x. When we apply the estimation theorem to this remainder, we find that its absolute value is less than or equal to 1 times the absolute value of x to the power of 2k plus 1, all divided by the quantity 2k plus 1 factorial. As we let k go to infinity, this upper bound on our error goes to 0 for any fixed value of x. Because the remainder term vanishes, the infinite series for cosine converges to the function itself for every real number x. A powerful feature of Taylor series is that we can combine them using standard algebraic operations, since they are a type of power series. This allows us to find new series without having to calculate derivatives from scratch. Let us look at the first example. To find the series for the function 1/3 times the quantity 2x plus x times cosine x, we first substitute the known series for cosine x. Then, we distribute the x and the 1/3 across the terms. Finally, by combining like terms according to their power of x, we arrive at the new series, which starts with x minus x cubed over 6. The second example demonstrates multiplication. To find the series for e to the x times cosine x, we write out the first few terms for each function. We then multiply them together, just as we would with two long polynomials, carefully distributing and collecting all terms with the same power of x. You can build new Taylor series from existing ones simply by performing ordinary algebra on the series themselves. We can generate new Taylor series from known ones using a powerful technique called substitution, which saves us from having to calculate all the derivatives of a new function. The principle is straightforward. If you know the series for a function f of u, you can find the series for a composite function f of u of x by simply replacing every u with the function u of x. This new series will converge for all values of x where u of x falls inside the original series interval of convergence. Let us apply this to find the series for cosine of 2x. We begin with the standard Maclaurin series for cosine of y(u). Then, in that series, we substitute 2x for every y(u). This gives us 1 minus the quantity 2x squared over 2 factorials, plus the quantity 2x to the 4th over 4 factorials, and so on. When we simplify each term, remember to apply the exponent to both the 2 and the x. The result is the correct Taylor series for cosine of 2x. This substitution method is an efficient way to expand our library of known series. Let us work through an example to see how we can determine the valid range for a Taylor approximation. The problem asks for the values of x, where we can replace sine of x with its first two non-zero terms, with an error no greater than 3 times 10 to the power of -4. The key insight here is that the Taylor series for sine of x is an alternating series. For such series, the alternating series estimation theorem provides a very convenient way to bound the error. It states that the error from stopping the series at a certain point is no larger than the absolute value of the very next term you did not include. In this case, we are using the terms up to x cubed over 3 factorials. The first unused term is x to the power of 5 divided by 5 factorials. Therefore, we set up an inequality where the absolute value of x to the 5th over 120 must be less than or equal to our desired error tolerance. Solving this inequality for the absolute value of x shows that it must be less than or equal to approximately 0.514. So this approximation for sine of x is valid within our specified error bound as long as x is in the interval from -0.514 to +0.514. This slide presents a figure that gives us a powerful visual for the convergence of a Taylor series. The main curve shown is the graph of y equals the sine of x. The other curves represent the Taylor polynomials for the sine function, such as p sub 1, p sub 3, p sub 5, and so on, with progressively higher degrees. The key pattern to observe is that as the degree of the polynomial increases, its graph hugs the true sine curve more closely and over a wider range of x values. For example, the polynomial p sub 3 of x, which is x minus the quantity x cubed over 6, is almost indistinguishable from the sine curve on the interval from -1 to 1. This visualization confirms what the convergence proof tells us. By adding more terms, we can build increasingly accurate polynomial approximations of a function. We will now outline the proof of Taylor's theorem, which provides the formula for the remainder term. The proof is quite elegant and relies on a cleverly constructed function and repeated application of Rolle's theorems. First, we define a new function, capital F of x, which represents the error. It is the difference between the original function, f of x, and an augmented Taylor polynomial. This polynomial is the standard nth degree polynomial, p sub n of x, plus an extra term, a constant k times the quantity x minus a, raised to the power of n plus 1. This extra term is designed to be 0, along with its first n derivatives at x equals a, so it does not disturb the matching we already have at that point. Next, we choose the constant k with a specific goal. We select k so that our error function f is also 0 at x equals b. Since f of a is already 0 by construction, we now have f of a equals f of b equals 0. This is exactly the condition we need to apply Rolle's theorem to the function f. The final step is to apply Rolle's theorem repeatedly. We start with f of x, then apply it to its derivative f prime of x, and so on, all the way up to the nth derivative. This chain of applications will ultimately reveal the value of k, which leads directly to the formula for the remainder term. We will now use Rolle's theorem repeatedly to find the value of our constant k, which completes the proof for the remainder term. We established that our special function f is 0 at both a and b. Rolle's theorem tells us its derivative, f prime, must be 0 at some point c1 between them. Since f prime is also 0 at a, we can apply Rolle's theorem again to the function f prime. This guarantees that its derivative, f double prime, must be 0 at some point c2. Continuing this process a total of n plus 1 times, we prove there must exist a number c where the n plus 1th derivative of f is 0. Next, we compute this same derivative directly from the definition of f of x. The result is the n plus 1th derivative of f minus the constant quantity n plus 1 factorial times k. Setting this expression equal to 0 at the point c gives our final piece. Solving for k, we find that it equals the n plus 1th derivative of f at c, all divided by the quantity n plus 1 factorial, which completes the proof. Let us bring together the main ideas we have covered about the convergence of Taylor series. The central concept is Taylor's theorem, which states that a function can be expressed as its nth degree Taylor polynomial plus a specific error term, called the remainder r sub n of x. The entire question of convergence hinges on this remainder. A Taylor series converges to the function that generated it if, and only if, this remainder term approaches 0 as n, the degree of the polynomial approaches infinity. To prove this, we introduced a powerful practical tool, the remainder estimation theorem. This theorem gives us an upper bound on the size of the remainder, which is essential for showing it converges to 0, and for estimating the accuracy of our polynomial approximations. Using this method, we established that the series for fundamental functions like e to the power of x, sine of x, and cosine of x all converge to those functions for all real numbers. Finally, these known series are valuable building blocks, as they can be manipulated to find Taylor series for new functions. To finish this section, let us look at 2 review questions that will help solidify the key ideas we have discussed. The first question asks you to use the remainder estimation theorem to show that the Maclaurin series for cosine of x converges for all real numbers. This is very similar to the proof we saw for the sine function. The central part of the problem is to determine an appropriate value for the constant, m, which bounds the derivatives of cosines. The second question tests your ability to manipulate known Taylor series to find new ones. You are given the series for sine of x and asked to find the first 3 non-zero terms for the function f of x equals the quantity sine of x squared, all divided by x squared. The strategy here is to first substitute x squared into the sine series and then perform the division. Please pause the video now and work through these 2 problems. They are excellent practice for applying these powerful techniques.